In section 3.8, we start getting back a little bit into the calculatory or mathematical aspects of this particular chapter in this particular course. And the concept that we delve into first here is called formula mass. Now, just to get kind of the nomenclature of this idea clear, what we're looking at with formula mass is a weight per unit of the molecule, or of the atom, if we are only looking at one atom. So we're looking at this first ratio here, AMUs per atom. And this is also synonymous with molecular mass and molecular weight. Now, if we want to talk about the grams per mole, this is this part, grams per mole ratio, then what we're looking at is called the molar mass, the amount of grams per mole of atoms or per mole of molecules. A lot of times you'll hear people mistakenly, and probably I'll do it too at some point, refer to these as each other, as a grams per mole weight as a molecular mass or vice versa. But here it is very clearly delineated which is which. Okay, so AMUs per atom, we're looking at molecular mass or molecular weight or formula mass. Okay. Grams per mole, we're looking at molar mass. So let's look at this. So for example, if we were looking at carbon dioxide, which we now know how to translate into CO2, we can just look up the weights under carbon and under oxygen on the periodic table. And we can add these up. And we can add them up in terms of one carbon at 12.01 AMUs per carbon and then we have two oxygens, rounding this to two significant decimals, 16.00 AMUs per oxygen. Okay, so we add this up, two of those, 32.00, one of these, looking at 12.01. The total here is 44.01 AMUs per CO2 molecule. Now, because of the mass that we picked for the AMU, effectively this is the same if we wanted to look at the molar mass, in terms of it will be 44.01 grams per mole of carbon dioxide molecules. Okay, so because of how we picked AMUs and the number of molecules in 1 mole, the numerical portion of this is the same regardless of which particular ratio we're looking at. So let's look at another molecule, C6H12O6. Okay, so 12 carbons, or 6 carbons, times 12.01 AMUs every 1 carbon, plus 12 hydrogens, and there's about 1.01 AMUs every 1 hydrogen. All right, we're just taking this number here and rounding it to a couple of digits. You can take the full values if you want, but a lot of times you only need 2 decimal places or 3 sig figs or 4 sig figs worth of significance here. 6 oxygens times 16.00 AMUs every 1 oxygen. Okay, and now we'll multiply those out. So 6 carbons, 6 times 12.01 gives me 72.06. Probably shouldn't have needed a calculator for that, but oh well. AMUs, 12 times 1.01 should be 12.12 AMUs, and 6 times 16 gives me 96.00 AMUs. So for the whole thing together, add 12.12, 96.00, and 72.06, and we get 180.18. We're adding here, so we have a certain number of sig figs that we're going to stay with. Let's see, 12.01. Technically, yeah, we only really have that first decimal there, so sig fig wise, we have 180.2 AMUs for every one C6H12O6 molecule. Or, in terms of molecular, that's the molecular weight. In terms of molar mass, number stays the same, only the units change. So 180.2 grams for every 1 mole of C6H12O6. All right, great. Now, what in the world am I supposed to do with this, right? We're going to look at things like counting by mass, right? Because all these things react in ratios with each other. I might have one hydrogen molecule and one oxygen molecule reacting with each other, but I can't really look and count the number of oxygens and hydrogens reacting with each other and see what they are. I can, however, weigh up certain amounts of substances by using a scale, and as long as I know how many individual objects there are for that amount or mass of them, then I can still get individual molecule to molecule ratios while still measuring in something that I can see, touch, feel, that kind of thing. So let's count using mass. If I have 10.8 grams of carbon dioxide, and I want to know how many molecules there are, well, then I just look at and add up the 12 and the 16 and the second 16 and get that 44 .01 grams of carbon dioxide. Let's double check that. Yep, 44.01 grams for every 1 mole of carbon dioxide. All right, so now we'll know the number of moles of carbon dioxide. So 10.8 divided by 44.01. So we have 0.245, and we'll cut it off here, 4 moles of CO2. That's not the answer. That's why we're giving more significant digits than we actually need right now. We only really can justify 3. But 0.2454 moles of CO2. We know how to convert between molecules of CO2 and moles of CO2. That's Avogadro's number, 6.022 times 10 to the 23rd. Molecules of CO2 for every 1 mole of CO2 molecules. And we punch that in on the calculator. So times 6.022 e to 23rd, and we get 1.4 into 3 sig figs, 8, right? 3 sig figs, 1, 2, 3, 1, 2, 3, 4. So this had 1, 2, 3. 1, 2, 3, 4 gives us 1, 2, 3. It's actually like 1.47779, etc. I get 3 sig figs, 1.48 times 10 to the 23rd. Cross off our units. Grams, grams, moles, moles. This many molecules of carbon dioxide. So now we can start relating things like how many of these react with how many of those, even though we can only count them by weighing out specific amounts on a scale.